Alright, so today we're going to learn about solving logarithmic equations. And before we do, we're going to just do a quick review of the properties. So it's important today that we can condense logarithms to one logarithm. So we're going to use the product property, but kind of in reverse. So if you have two logarithms separated by addition, you can bring them together as a single logarithm by multiplying those arguments together. And then if you have two logarithms separated by subtraction, we can bring them together using division. So that is something we're going to use today on some of these problems. Another thing that we need to revisit is the idea of extraneous solutions. So an extraneous solution, if you guys remember back from like August when we talked about this, but extraneous solutions are false solutions. And on these particular type of equations, the false solution is going to come when you plug the value back in, but it makes the argument negative. So it's not, the value you get is not in the domain of the problem. So one thing to keep in mind when you're checking these for extraneous solutions is that the argument cannot be negative. All right, and the argument of a logarithm, like log base v of a, that's the argument. You're taking the logarithm of. Okay, so there's two types of logarithmic equations, and depending on what type it is, that's the process you go to solve it. So type 1 is when you have log equals a log. And when you have log equals log, you're going to drop off the logs and solve. Now, solving it might be a quadratic equation, it might just be a linear equation, it might be a radical equation. There's all different types. So the dropping out the logs is the first step to solve another equation. Right? The other type is when you have log equals a number. Right? When you have log equals a number, you do something that I like to call raise the base. Right? Now the technical mathematical term for it is to exponentiate. So let me show you what I'm talking about. So if we have log base 2 of x equals 3. This is a log equals a number. So raising the base or exponentiating means taking the base of the problem and like raising everything up. So 2 is the base, and then its exponent is going to be log base 2 of x. And then you do the same thing on the other side. 2 is the base, its exponent is 3. Now the whole purpose of doing that is because when you have 2 to the log base 2, that's a property we've talked about for a few days, but that basically cancels out and just leaves you with x equals, and then 2 to the third on the right side is 8. So that's raising the base, and we'll do several of these. Okay. So the first thing we want to do is isolate our log or solve for log. So on example 1, we would go ahead and add the 2 to both sides. All right. Then the other 2 in the problem, we would divide by it. And I'm just going to leave that as 19 over 2 because it doesn't go evenly. There's no reason to get a decimal. All right, so then this one is type 2. This one is log equals a number. So we are going to raise the base. Or exponentiate, whatever you want to call it. So if it's natural log, what is the base? So natural log, the base is e. So we have e to the natural log of 3x equals e to the 19 halves. All right. So the whole purpose of doing that is to cancel out the natural log, and the 3x comes down. Now there's no way without a calculator that we can figure out what e to the 19 halves is, so we're just going to leave it e to the 19 halves. All right, and then our last step is to divide by that 3. Now this is exactly how I would want you to leave your answer. Because we can't use a calculator, we cannot figure out what that is. So that's it, that's the answer. Now we do want to make sure when we plug that back in for x that it doesn't give us a negative argument. Well, it's not a negative value, so there's no way it can give us a negative argument when we plug it in here. And then multiply it by 3, it's not going to be negative, so we're good. Okay, so let's look at B. All right, this one, the log is already isolated. We just have the log of the square root of x plus 2. So this one is type 2 again, because log equals a number. So we'll raise the base. All right, so this time our base is 3. So we'll have 3 to the log base 3 of the square root of x plus 2 equals 3 to the first. So I'm just taking the original problem, and those become exponents, and whatever your base is the big base. Okay, and then the whole purpose of that is because 3 log base 3 cancels out. We're left with the square root of x plus 2 equals 3 to the first, which is 3. And then we're going to solve it for x. So how do you get rid of a square root? You get rid of a square root by squaring both sides. All right, and then we'll subtract that 2, and our answer is 7. But we need to make sure when we plug it back in, it doesn't give us a negative argument. So when we plug it back in, we're going to get the square root of 9, which is fine. It's not negative. All right, let's look at C. Hopefully my Apple Pencil won't die before then we get finished with it. So on this one, we have log plus log equals a log. So before we can do one of the types, we do need to condense these logarithms. So we have 2 logarithms separated by addition. We can bring it together as one logarithm, and I would multiply those. Ooh, another thing that we need to do on this side is move that 2 up to a power. Okay, so I will go ahead and multiply that together. Just using the distributive property. All right, and then this one is type 1. We have log equals a log. And when you have log equals a log, you're going to drop off the logs. So we just have 2x squared minus 7x plus 6 equals x squared. Okay, so this is a quadratic equation to solve, and I'm going to solve it by getting everything on one side, and then hopefully it will factor. So that's my favorite way to solve quadratic equations. And it does factor to x minus 1 and x minus 6. All right, so we originally get two answers, 6 and 1, but let's make sure that they're really answers. So we have to plug them into the original equation. We plug them here, here, and there. So when I put 6 in, we're just making sure that the argument's not negative. So when I plug 6 in, I get 4, positive argument. When I plug 6 into the second x here, I get 9, so that's fine. And when I plug 6 into the third one, I get 6, which is fine. But when I plug 1 in, I get -1, and I get -1 again for my argument. So 1 is not a solution, but 6 is. Number 1 is extraneous. All right. So let's look at D. For D, again, I need to condense these logarithms. So since they're separated by subtraction, I'll use division to bring them together. All right, so this one is also type 1 because I have log equals a log. So I'm going to drop off the logs. And then I have a rational equation to solve. It's been a little while, but we can do this. Okay, so if we need to solve an equation and our x is in the denominator, we can't solve it when x is in the denominator, so we're just going to multiply by it. So we end up with x plus 7 is going to equal x plus 1 times x plus 3. Right? And then that's going to be x plus 7 equals x squared plus 4x plus 3. All right, and it's another quadratic equation that we'll solve by getting everything on one side. So I subtracted x, and then I subtracted 7. All right, and then this one will factor, yep. All right, so we originally get two answers. It's unlikely that there are two, but there might be, but we need to check to make sure. So when I plug in -4, I'm okay here because that would give me 3. But when I put it here, that's going to be -1 for your argument. And when I put it here, it's going to be -3 for the argument. So -4 is definitely not a solution. It's extraneous. But 1 looks like it works out fine because you're adding 1 to 7. 3 and 1 is always going to be positive. So we're good for 1. All right, that's solving equations that involve logarithms. All right, we are going to do one application problem. So for example 2, the number y of endangered animal species on a protected wildlife preserve can be modeled by that equation y equals -117 plus 159 natural log of t, where t is between 10 and 24, and t represents the number of years since 1990. So that would mean that 10 is 2000 because you add 10 to 1990. All right, how many years since 1990 did the number of endangered animal species reach 342. And then we're going to leave this in exponential form because we won't have a calculator to figure it out. All right, so all this is telling us is to take this 342 and plug it in for y. That's the number of endangered species. That's what y is. Okay, and then we're going to solve this equation for t. So first, we want to isolate the logarithm. So I would add that 117. All right, and then I would divide by the 159. All right, and 3 divides evenly into both of those numbers, so that reduces down to 153 over 53. All right, and then this equation is log equals a number, so it's type 2. So we're going to raise the base. Come up here. So since it is natural log, I'm going to flip the order, so hopefully that doesn't confuse you. Our base is e, so e to the natural log of t equals e to the 153 over 53. All right, and don't forget the whole purpose is to cancel out the log, and you're just left with t equals e to the 153 over 53, and this is a number of years. All right, and then we can see how many years that is if you are curious. I'm hoping you're a little bit curious. So if we do e to the 153 divided by 53, that's going to be 17.9357 years since 1990. So like 2007. All right, so I want you to do this one extra problem that I put down here because the book didn't have really great applications to do without a calculator. So you're going to do this problem and you're going to do page 235, 46 through 54, even, 57, 60, and 61. And I'll have that typed on Google Classroom also.